Hello and welcome to Chapter 7 of the AP Bio Exam Review video series. Today I'm here with Penelope the cat. She might start talking. You want to say hi, kitty? You want to say hi? She's mute right now, but maybe a little later. But today we're going to talk about cellular respiration and fermentation. Okay, you must know the summary equation of cellular respiration according to the source and fate of the reactants in the products. What's important about this statement is what you don't need to know. What you don't need to know is every single intermediate of all of those chemical reactions, which means you don't have to memorize citric acid cycle, you don't have to memorize all the equations of glycolysis. You need to know the summary of each of those individual constituents. All right, so here is the summary reaction. And to point out a few significant items about this reaction, here is going to be your glucose, and that is going to join oxygen, and that's going to produce CO2, H2O, and of course that energy. And of course that energy is going to be in the form of ATP. We're going to notice that this is going to be a series of redox reactions, and so your glucose is becoming oxidized and your oxygen is becoming reduced. And we're remembering that when we say things become reduced, that means they're gaining electrons, and those electrons are traveling with hydrogens. So if we follow the hydrogens, we're able to figure this out. And so if we're adding electrons, we're adding hydrogens. Kitty is very jealous that I'm paying attention to the iPad and not to her. So we follow the hydrogens, we add the hydrogens from the water here. That's how come this is being reduced. And the hydrogens are being lost to form the CO2, and that's how we say that becomes oxidized. All right, I'm scratching Kitty's chin with my left hand and writing with my right hand, so hopefully that'll be enough to satisfy the beast. Okay, so overview of cellular respiration. Of course, the bulk of these reactions are actually happening in your mitochondria, and that's what this kidney bean shaped thing is represented here. And then outside in that orange box, this is just the cytosol of the cell. So they're not showing you the cell membrane or anything like that. There's some pretty important stuff that's happening in the cytosol before we move into the mitochondria, and that's this glycolysis stage. You're going to remember that glucose is going to be your 6-carbon sugar. We're turning that into pyruvate, which is your 3-carbon sugar. And in doing so, we are going to produce a little bit of ATP, and we're going to produce a little bit of NADH. Remember, NADH is the electron carrier that's going to take the electrons from glucose into our electron transport chain, which is at the end of what happens in our mitochondria. And so the glycolysis phase is really preparation for the rest of cellular respiration. Not a lot is produced there relatively, but it's getting that molecule of glucose ready to go into the citric acid cycle. We don't want to also neglect pyruvate oxidation. Pyruvate oxidation is super important because it's what's preparing pyruvate by oxidizing it into acetyl-CoA to actually go into that citric acid cycle. But that again is happening as the pyruvate is going into the mitochondria. So to look at it as an overview, the majority of your NADH and FADH2, your electron carriers, are coming from the citric acid cycle. And then, of course, the majority of your ATP is actually coming from the electron transport chain. Notice that it says oxidative ATP, so that's oxidative phosphorylation is happening there, versus substrate level ATP production earlier. All that means is that it's an enzyme that's actually adding an inorganic phosphate to ADP in these two earlier stages. So all that being said, I mean, this is the overview. Getting this in your head is absolutely crucial as far as the level of understanding College Board expects out of you. And so, spending some time with this diagram is certainly useful. Okay. You must know the role of glycolysis in oxidizing glucose to 2 molecules of pyruvate. So this is our first step in that cellular respiration process, and also in fermentation for that end. All right, so this is how you produce ATP using an enzyme, and it's just called substrate level phosphorylation. And all that means is that ADP, here we go, and just a general molecule with a phosphate attached to it comes into the enzyme, and that enzyme essentially facilitates the move of that phosphate over to the ADP to produce ATP. And this product, like I said, is just a general molecule that brought in this phosphate from earlier. So this is called substrate level phosphorylation. It's It'll produce ATP very clearly. I mean, that's what the diagram is showing you. But as far as the amount of ATP it produces, it's not much ATP. Really, the electron transport chain is the most effective way to produce ATP for your cells. So when we look at glycolysis, okay, there are two phases. We have what's called the energy investment phase, and then we have what's called the energy payoff phase. And so in order to essentially get this whole process started, we have to invest 2 ATP into this process. In some of those intermediates that I told you earlier, you don't have to actually know. But we invest 2 ATP, and then in the energy payoff phase, we actually are producing 4 ATP. In addition to 2 NADHs. Remember, the NADHs, those are your electron carriers. All they're doing is carrying the electron from the glucose over to the electron transport chain, which is going to allow lots of ATP to be made from every one of those hydrogen atoms. So in sum, what we end up with is 2 pyruvates and 2 water molecules. Okay, that's coming from our glucose, but we're also net profiting 2 ATP and 2 NADHs. And what that essentially means is that we're getting a little bit of energy at this phase, but just really not very much. You need to know how pyruvate is moved from the cytosol into the mitochondria and introduced into the citric acid cycle. So this is pyruvate oxidation. It looks like I covered up my N. This is pyruvate oxidation, and all that's saying is that here we have our pyruvate. This is the double membrane that is the mitochondria, and as it moves across that double membrane, we are actually producing our first molecule of CO2. So we're going from a 3-carbon sugar to a 2-carbon molecule. We're adding on a coenzyme called coenzyme A, producing what we now call acetyl-CoA. In doing so, we actually produce one more molecule of NADH, and that, of course, is going to go to your electron transport chain. So this is not part of the citric acid cycle, okay? This is called pyruvate oxidation. In some textbooks, they call it the preparatory reaction. It's very vague as far as I'm concerned. It really is pyruvate oxidation. It's really actually what we're doing. And at this point, acetyl-CoA is actually the molecule that is able to go into the citric acid cycle next. We'll focus a little bit more on the citric acid cycle in a couple more slides, but I do like how this diagram just shows you, in general, what happens is each of those CO2 or each of those carbons comes off in the form of CO2. They don't come off together, they come off separately, and I'll show you that in a second. And through the cycle, we are able to produce 3 NADHs, 1 FADH2, as well as an ATP. This is still substrate level phosphorylation, so this is not electron transport chain, we'll get to that later, but we're producing one molecule of ADP, or ATP rather. Really what the benefit of the citric acid cycle is that we've managed to get rid of all of that carbon, and we have produced 4 electron carriers, 3 here and 1 here. And that's like money in the bank. Those electron carriers are going to take those electrons over to the electron transport chain in order to use them to produce ATP. So here is the citric acid cycle in its entirety. This is not what you need to know. I'm just showing you this because I want you to understand that the carbons come off separately here and here, and that the NADHs and the FADH excuse me, are produced independently. And so we don't produce all 3 of the NADHs at the same time. In the end, it is a cycle, and so we have to end with the same molecule that we start with, and that's what you're seeing right here. Do not try to memorize this. Not even kind of. I would be really disappointed if you spent your time when prepping for the AP test in memorizing this cycle. All I need you to know is that we go in with 2 carbons. Those carbons are lost, ultimately, and we produce these electron carriers here, here, and here, as well as an ATP in this process. You have to know how those electron carriers work. Okay, that's what this is saying. You need to know how electrons from the NADH and the FADH2 are passed to a series of acceptors to produce ATP. So I like this diagram, and the analogy I used in class was to say, you go to the gas station, you put gas in your car, and if all of the energy, the potential energy that's in that gas is released at once, your car would explode at the gas station. Excuse me. And that's not what happens, and that's a good thing. That's a good thing that that's not what happens. Well, something very similar happens with the electron transport chain. With the electron transport chain, we slowly release the energy, the potential energy that is harnessed in that electron as it goes down the electron transport chain. And as we slowly release that energy, we're able to produce ATP. The way we're able to produce ATP is by producing a hydrogen ion gradient, and I'll show you that again here in just a second. But just kind of keep that analogy in mind. The electron transporter, that NADH, the electron carrier, NADH, drops off the electron, but rather than all of that potential energy to be released at once and having a little explosion, instead it's gradually released, and we're able to harness that to produce the ATP. So this is what it actually looks like. The CYTs that you see here are called cytochromes. Okay, they're just proteins, and we group them in these complexes 1, 2, 3, and 4. Essentially, all that happens is your electron transport or your electron carrier drops off the electron here. Okay, and then as it does that, we have a series of redox reactions as we go down this chain. Each one of these proteins is slightly more electronegative than the one before it. And then, of course, we end with oxygen, which is our extremely electronegative molecule. And so, because we have slightly greater electronegativities, as we fall down this chain of proteins, our free energy is always, our delta G is always negative. You can also see here that NADH is dropped off in protein complex 1, whereas FADH is dropped off in protein complex 2. And that means that NADH is actually able to make more ATP per molecule than FADH is, just because it has a longer time to be able to produce that hydrogen ion concentration gradient, which I'll show you here in a second. You need to know the roles of the mitochondrial membrane, the proton gradient, and the ATP synthase in generating that ATP. Okay, so now we're going to actually look at the cartoon of the electron transport chain. On the previous diagram I showed you, over on the y-axis was actually showing you the change in free energy. It's actually all embedded in a membrane, okay, in the mitochondrial membrane. It looks more like this than in that previous graph image that I was showing you. And what's happening is just like I was showing you before, we drop off our electron, and as we move down those proteins, those cytochromes that are kind of now hidden in these protein complexes, as we do that, we are pushing hydrogen ions across, or not over here, we're pushing hydrogen ions across the membrane. Well, we're pushing them, we're using energy in order to do this, we're moving them against their concentration gradient, so now we end up with lots and lots and lots of hydrogen ions over here and very few over here. So they're going to want to diffuse back down their concentration gradient. The trick is, the only path they have to get there is through this thing called the ATP synthase. And what the ATP synthase does is, as that hydrogen ion is coming through, it harnesses that power of diffusion and produces an ATP. This part is called the electron transport chain. This is called chemiosmosis. Osmosis is just that diffusion, and chem means it's a chemical. So chemiosmosis is how we're actually producing this ATP. And this whole process is called oxidative phosphorylation. So we're using oxygen. Remember, that's the very end of the electron transport chain. It's right here. And we're using that to add a phosphate to the ADP. So oxidative phosphorylation is where that term comes from. This is a zoom in of the ATP. Don't obsess too much about how this guy works. That's not a part of your curriculum, but sometimes it's easier for you guys to understand what's happening if I actually just give you a little bit of an image. So here what happens is, and I told you before, the hydrogens want to come back across the membrane, and they want to do that because that's down their concentration gradient. But as they do that, the only way for them to get through is to go through this little channel. And as they go through this little channel, what happens is they spin around this guy here. We call it a rotor. They spin around this guy here, which is spinning this thing, except this part is being held still by the stator, this guy here. So this is spinning, this is spinning, this is being held still. And so it's kind of like, I don't know, twisting a phone cord but holding one end straight. Like you end up kind of coiling. Well, the power of that coil essentially is what is used to take the ADP and attach it to that inorganic phosphate. As soon as this guy makes the full turn around, it is ejected and it is essentially gone back down its concentration gradient and it's happy as a clam. Chances are good back over here with the electron transport chain, as soon as it's going to be sent back out to do the whole thing again. Okay, so to put the whole thing together, here's glycolysis, where we produce our 2-pyruvate, but as far as energy is concerned, we produce 2 ATP from substrate level phosphorylation, and then we have 2 NADHs. Those NADHs are kind of like money in the bank. We can't spend that energy yet. We have to send it through the ATP or through the electron transport chain to turn it into ATP, but it's money in the bank. That is going to cross into the mitochondrion, because remember, this isn't any good unless it gets to the electron transport chain, which is actually in the mitochondrion. It's right here where some of this variability happens about how much ATP per glucose can be produced. There are these electron shuttles that are right here, which means this NADH doesn't actually go in. It essentially drops off its electron, and then an electron carrier here picks it up and goes. It could be either NADH or FADH2, depending on which one just happens to be there. But because they drop their electron off at different places in the electron transport chain, if the NADH becomes an NADH here, then we're going to get the 32 ATP. If the NADH becomes an FADH2 here, then we're going to get the 30 ATP. So that's pretty much where that variability is coming from. And it just, like I said, it just depends on what's available in the mitochondrion at that time. The 2-pyruvate go through pyruvate oxidation as it enters the mitochondrion. It produces 2-acetyl-CoA. When this happens, we've actually kicked out one of the CO2s, or one of the carbons in the form of CO2. We've produced 2 NADHs. It's going to go to the electron transport chain. Your acetyl-CoA is going to go into the citric acid cycle. Here we're going to eject 2 more carbon molecules in the form of CO2. We're going to get 2 more ATP in the form of substrate level phosphorylation. But we're also in here going to produce 6 NADHs and 2 FADH2s. If you're confused because earlier I was saying 3 and 1, it's because that was per pyruvate, and we need to remember that glucose becomes 2-pyruvate. So that's why we have 6 and 2 instead of 3 and 1 there. So then we have 2 NADHs, 6 NADHs, 2 FADH2s, and then 2 of something else that all go into that electron transport chain that produces in sum 26 or 28 ATP by oxidative phosphorylation, and that's how you get your total of 30 to 32 ATP. Okay, you need to know the difference between fermentation and cellular respiration. So, no matter what, glycolysis is going to happen. Glycolysis is not oxygen dependent. The rest of the whole process that we just talked about is oxygen dependent because we have to have oxygen at the end of the electron transport chain in order to make ATP. So you can always go through glycolysis in the absence of oxygen and produce 2 ATP in the form of substrate level phosphorylation. This is not very efficient because 2 ATP is not much. However, if you're in a pinch, this will do the job very nicely. So in this case, when we look at fermentation, we're showing alcohol fermentation as well as lactic acid fermentation. This is the one that yeast do. That's how they produce beer and wine and whatnot. Lactic acid fermentation is what happens in your muscles when you're working out hard. And essentially what's happening is that as we go through this process of glycolysis, when we get to the end, we have the pyruvate. That's what glycolysis is meant to do. Except that in alcohol fermentation, that pyruvate is then turned into this 2-acetylaldehyde, which is then turned into ethanol, which is then what we drink in beer or wine. But this is just a cycle of of NADHs and NAD pluses, because remember that glycolysis is also producing these 2 NADHs. And so then we're able to then reduce this, or oxidize it back into this and reduce this, I suppose, in producing ethanol over here. Same thing is happening over here with lactic acid or lactate. The pyruvate, of course, glucose becomes pyruvate. That's what glycolysis is, and in doing so produces 2 ATP and 2 NADHs. But then in order to get back what you started with, we turn our pyruvate into lactate, and of course there's a lot of chemical reactions that are hidden in that arrow. And then this lactate builds up until ultimately you can process that and turn it back into pyruvate, actually, that can be used by your body. But it's an acid, and that's why it hurts when you build that up in your body. So fermentation is just using glucose to produce energy, ATP energy, not much of it, again, only 2 ATP, but produces energy when you're in a pinch and you just don't have enough oxygen to do the oxidative phosphorylation that would be better. Pyruvate is really the juncture in catabolism. So what that means is that this is going to happen one way or another. The question is, at this pyruvate step, if oxygen is present, then we're going to go into the mitochondria and do the citric acid cycle, the electron transport chain and whatnot. If there's no oxygen present, then we're going to go into the ethanol or the lactate or whatever it is for that organism. But it's this step, it's right here, where oxygen being present or absent really directs where that molecule goes. All right. Clearly I am sick, so thank you for bearing with me as I try to make this video. I hope you learned something through all my coughing, and I hope you have a good day. Bye.